This is Mrs. O'Neill for AP Chemistry, Chapter 19, Section 3, Molecular Interpretation of Entropy. So in this section, you're going to appreciate on the molecular level the entropy of a system that is related to the number of microstates. So you're going to know that entropy of the system increases as the randomness of that system increases. And now the third law of thermodynamics states that at 0 degrees Kelvin, or I should say 0 Kelvin, not degrees, the entropy of a perfect crystalline solid is actually 0. Because again, you always need some kind of standard. You need somewhere where it says this equals 0 because, and then you base everything off of that. So this is Mr. Boltzmann. He gave us this conceptual meaning of entropy. So I always like to kind of show you when he lived and what he did and a picture. So we want to remember that entropy is defined in terms of probability. And that's what that whole, again, entropy explained with sheep thing was. So again, if you did not get a chance to read over that or look over that, you might want to pause the video and go to that first. So we're going to calculate the number of arrangements for a system, or the number of ways things can be arranged, like the sheep, like I said before, in that other reading material. So if we have one atom, and here's our two chambers, kind of like that gas chamber we looked at before as well, there's a 50-50% chance that the left side is going to be empty. Okay, so again, just where is the possible places that one atom can be? Well, in this case, there could be two arrangements. Either that one atom's in the right or the one atom's in the left. That's it. However, if we have two atoms, look at the possible arrangements. Now we have a 25% chance of the left side being empty because the other 25, the other 75% chance, there's going to be something in that left chamber. But notice how, again, we have 50% of them being evenly distributed. So two things to look at. We have the fact of where are those two atoms? Are they together? Are they separated? And again, how often are we going to find that chamber being empty anyways? So you went from one atom with two arrangement to two atoms with four arrangements. Oh my goodness. Now all we did was add two more atoms and now we have 12 possible arrangements. So as you can see, as we build up the number of atoms, the possible arrangements are going to very, very quickly add to the amount of possible arrangements. So that's what that guy did, that Boltzmann, and that's where he came up with that graph as well. And that's where the sheep come in. So hopefully that between those two things you're understanding. So pause the video, fill in your notes, and then play to hear my words. So we want to understand that a molecule or an atom has three different kinds of motion. There's a translational motion, which is the entire molecule moving. There's vibrational motion, where the atoms within the molecule are kind of moving toward and away from each other. And then there's the rotational motion, which just means that the molecule is spinning on an axis. So here we have some pictures. So you might want to make some drawings here just so you're understanding what's going on and have that visualization. So here's translational motion, where you have a whole molecule. It's staying as that molecule in that same orientation, as you will, but as it's moving along the path, that's the translational motion, is just that same exact molecule just moving along a path, but in that same orientation. Then you have something like vibrational motion. And again, it's talking about, let's say, H2O, and it's talking about those atoms are kind of moving in and away from each other. So here are some examples of other vibrational motions in our lives. And rotational just means that we have basically an axis in the middle of the molecule and it's kind of just revolving around it. So here's all three. Again, if you want to pause the video, make sure that you're understanding those three different kinds of motions, what they mean, and what they represent as far as an atom or molecule. So can you label which one is which just by looking at these pictures? And hopefully that makes sense, as well as I try to do things in order so it's easier to picturize that stuff. So give it some thought. Hopefully that makes sense, right? You're going to vibrate and you're going to rotate, but you're not going to necessarily, those are the two that you cannot do, right? You're not going to vibrate and rotate because it's only one molecule. There's no such thing. But it still can be translational, though, because that one molecule, obviously, or that one atom is moving. So here are some other examples of microscopic radiation and spectroscopy radiation, and it's just giving you that idea of how they move. And again, down here on a molecular level, they're going to talk about the different ways they move. Here's the molecular, vibrational, rotational. So I saw this and I thought this was neat to show you. So what is the third law of thermodynamics? Again, every value needs a starting point. Every value needs that zero. And how do we get the zero for delta S? How do we get the zero for entropy? Well, a perfect, pure crystalline solid would have a zero entropy. Can you answer this? That's exactly what we said. So I wanted to, again, give you a picture representing that. So if it's all lined up and it's a perfect crystal, it's not going to have any entropy. It has to have a starting point. Okay, see you in class.